So I will just get started. And yeah, I think you have already learned a lot from the pre-processing from Abby. So once you have picked your particles, how do you get the 3D reconstructions, the structure of your proteins at near atomic resolution, hopefully high resolution, using the pipeline we build or workflow we build in nextPYP. So here I'm just gonna talk about the outline. First, we are going to talk about the scalable and lightweight architectures Edward just mentioned in the introductions, and how we can bypass the extraction of the solid volumes and the particle stack so that make everything, we don't need to store a bunch of or a lot of solid volumes or particle stack that may become a bottlenecks in the data processing. And I'm gonna talk about the types of blocks we define after the pre-processing for the refinement. We have different types of block. Each has its own responsibility and how you can connect different blocks flexibly and change the parameter to do your experiment. And then followed by the constraint high resolution refinement. I'm gonna talk about what kind of parameters you are going to refine and what can lead you to high resolution structure determination. And then lastly, I will talk about the constraint classification. If your data or your protein has different conformation or they have different motions, we can classify your protein to resolve the conformational heterogeneity using constraint classification, and what's our panel or what's the result you can get and to troubleshoot or to visualize your result in nextPYP. So here are, before talking about the scalable framework, now we all need to do the solid volume averagings. Traditionally, we need to do the solid volume averagings. First, we are going to have like a lot of tail series. We reconstruct the tomograms from the tail series, and we pick the particle, get their particle locations, and we extract the particle into a lot of small cubes. We call it subvolumes, and align the subvolumes against the reference and align all of them against the reference. And the process we call is subvolume averagings, and it will be done for multiple iterations until we get the high resolution structures. I want to highlight here, we need to store a lot of subvolumes. If the data set get larger, it's pretty critical because we know we got a low signal to noise ratio for the tomographic data sets. We need more particles. So the data set will only get larger, will not get smaller. Then we need to store a lot of subvolumes. So this is a typical example. It may become a bottleneck in the data processing. A data set called HIB1 gap proteins is on the Empire database. It has 43 tail series, about 3,000 particles per tail series. And for each particle, it has 41 tilted projections. Each projection has about 10 frames. And if we are going to use 384 as a box size, for each subvolumes, it will be 384 cubes. So I will just do the math for you. If we are going to store this amount of subvolumes, it would take about 20 gigabytes, which essentially will become a bottleneck for a modern computer. And at the same time, we are not just processing one data set, we might have multiple data sets. So it is not a practical thing to do using this strategy. So here we just come up with the solutions to better use the computing resources more effectively. First, on the left-hand side, you still see multiple tail series, and we define the bundle as maybe one. It is made up of one or more tail series. So each bundle will be assigned to one computing machine. So each color represents one computing machine. So, and then in order to bypass the extraction of the subvolumes, we extract the particle from the raw tilt images, so it will be a particle stack and not the subvolumes. And then we align the particle stacks using CSPT constraint refinement by aligning the particle stack with the constraint of tail series alignment parameters like tail angles. And for each bundle, each computing machine, when they are done, each will generate intermediate reconstructions And once all the processes are done, we merge all the intermediate reconstructions into one merge reconstructions, and it will be used as a reference for the next iteration. So it also done in multiple iterations. And I just want to highlight here, you see there's like a temporary scratch storage. You can think it's like a cloud somewhere on the cluster, and you don't necessarily need to store your particle stack in your computing machine. So you don't need to store the particle stack and the salt bombs. So it will be small storage footprint. The storage of the particle stack will not become a bottlenecks in the data processing. And also want to highlight the scalability. Let's say if your data set get larger, you have more tail series, you can usually, if you have enough resources, you can add more, like, for example, one computing machine to this stack to make all the data processing parallel. So it will be very scalable and it is not blocked by the size of the data set. So you already see some kind of like mechanism from the previous session. So we usually have a launch. It will kind of divide the data set into several bundles and send it to different workers or different computing machines. And each computing machine would handle the alignment and the generation of the intermediate reconstructions in each split job. Once they are all done, the merge job will merge all the intermediate reconstruction into one merge reconstructions. And at the same time, if there are some fail one, like due to if there are something fails, it will relaunch the fail one and then try one more times to wait for the result to complete. Right. So here's the gains from the scalable architectures, the same data sets. It has 43 tail series. The refinement will be done more efficiently because we kind of process the data in parallel if we have multiple machines. And the total storage requirement will be reduced to less than 1 gigabyte, essentially just the raw data and the metadata, which is way better than 20 gigabytes. So we kind of make it more scalable and the small storage footprint using this scalable architectures. And you are going to see that all the time during the refinement. So the refinement, how to get high resolution structures by aligning the particle projections. First will be refinement, and refinement essentially there's like different kinds of refinement. First is the reference-based refinement. This means to get the initial orientation, particle orientations. And secondly, we have fully constrained refinement. It's meant to refine the tail series alignment parameters we was previously resolved or get obtained during the pre-processing. And we also have the region-based refinement to address the local motions during the exposure. And we are also able to refine the per particle CTF we are done during the pre-processing to further improve the map resolution. And we also have the particle filtering, which allows you to filter bad particle or duplicate particles. And we also provide you the way to create a shake mask so that you can apply the shake mask on your reference so that you are not aligning the noisy background during the alignment. And if your data have frames, like each tooltip projection has multiple frames, you can also align the frames, refine the motions across the frames into a movie frame alignment. And once you have the high resolution reconstructions, you can sharpen your map using some bit factors in the post-processing. So this is how it looks like in nextPYP. Before this session, you already see we have import raw data block and the pre-processing block. And once you have the pre-processing block and you have multiple particle picks, you can click on it and to create a particle refinement block. It's usually the first block after the pre-processing. You can do reference-based refinement, fully constrained refinement, or region-based refinement, or per particle CTF refinement in the particle refinement block. And then if you have a bad particle you want to get rid of, you can create a particle filtering block to get rid of bad particle. And if you want to create a shake mask from using the reconstruction you just have from the particle refinement block, you can also create a shape mask in the masking block. And if your data have frames, you can easily create a block that is specifically for the movie frame refinement. It's called movie refinement block. And once you have the reconstructions, you can create a post-processing block to sharpen your mask. And how to create a block, I will show you tomorrow in the practical session. But essentially, in the block, you just click on the bottom right. There's like a small icon. Once you click it, it will like pop up a menu that there are several blocks that you can create it based on the current block. In this case, you have post-processing, masking, refinement, and particle filtering and movie frame refinement from the particle refinement block. So this diagram will be simplified version. You can easily contain or customize your workflow. It doesn't have to be looks like this. And just to simplify the workflow, I'm gonna use this diagram to show you the steps and different kinds of blocks. So first would be refinement, reference-based refinement. And in order to get the initial alignment particle orientations, we use the external reference to find the 6 parameters of the particle orientation, 3 for rotation and 3 for translation. And it will search exhaustively in the entire landscape of the 6 parameters. We know it's time consuming, but if you have you already know some kind of particle orientations, such as envelope spikes that maybe you used our geometry-based particle picking, you already know some initial orientations where the spikes are vertical to the membrane, for example. You can use like fewer points or narrow range to not search that such extensively. And there are some critical parameters. Obviously, you need to provide a reference. The reference can be downloaded from EMDB and database, or it can be reconstruction. You use other strategies such as a single particle, and it can be just low resolution. And then other critical parameters, minimum and maximum resolution for all the refinement and alignment. And we only, by setting this parameter, especially max resolution, we only align the frequency or the information within the range from the main resolution to a max resolution. And then when we are getting the particle or refining the particle orientation, there's like another 2 parameters pretty critical. First one is first exposure for the refinement, and another one is last exposure for the refinement. And look at the diagram on the right-hand side. Essentially, we want to use the tilted projection of a given particle, which have high quality. Essentially, it's something around a 0 degree. And this number depends on how you collect the data, whether you collect it from -60 to +60, or you use a dose symmetric scheme. Then essentially you just use the range that has best quality. And then once you get the initial particle orientations, you can use the reference we got from particle refinement or reference-based refinement to refine the tilt series alignment parameters, which is made up of tilt angles, tilt axis rotation angles in plane rotation, and the tilt translation in 2D. And by aligning the particle projections present in a given tilt to the projections. And once it is refined, you can go back to refine the particle orientations using CSPT. And there are still some critical parameters. Go to the constraint refinement tab in the particle refinement block. You need to click on these 2 options. If you want to refine the tilt series alignment parameters, you need to click on these options like refine tilt geometry. And if you want to refine the particle alignment parameters, you need to click on these options. And there's more advanced options like the range you want to search for rotation and the translation. I'm not going to go into these details, but you can also set them up if you don't want to search that wide range. So in order to address the local motions happening during the exposure, we have region-based refinement to address this problem by having additional parameters to kind of describe the local sample motions. So essentially, we divide the tilted projection of the tomograms into several patches or several regions. Each region has its own tilt series alignment parameters or its own parameters. So we can kind of model the sample motions separately for each regions, and not just the local sample motions. We can also optimize the CTF parameters by moving the Z or all the particle projection in the Z dimension up and down to refine the defocus and astigmatisms. And it would allow us to have more precise alignment parameter and CTF parameters and improve the improve the map resolution while preventing overfitting, because we still have your particle in each patch. So the particle presented in each patch will be aligned together, so to keep the constraints. Then we will not fall into overfitting regimes. So once you try to align your particles, there are still some bad particles in your reconstructions, and you don't want them to be in your reconstruction. You want to use a good set of the particles. So we can kill your particle or filter your bad particle in the particle filtering block. So after the refinement or alignment, your particle may still not be properly aligned, or they can, maybe the particle you pick are not true particle. They are like some other proteins, or they can be too close to each other, and the alignment brings the particle to its neighbor. That would end up having the duplicate particle where you have the same position, same orientation, that result in cross collation overfitting in the FSC. So we need to get rid of the bad particle during the particle refinement or particle filtering block. In the particle filtering block, you should always see the score that you can use it to determine or choose your threshold to get rid of the bad particle, because the bad particle tend to have lower score in these histograms. And there are still some critical parameters for the particle filtering. And as I mentioned, you have the score threshold. You can use the histogram in the particle filtering block to determine the threshold you want to get to get rid of the bad particles. Normally, you should see two populations or two distributed population in the histograms. Then you can select the threshold between these two populations to get rid of the particle that has lower scores. And then another one is mean distance between particles. It will be in pixels. So in order to get rid of the bad particle, they are too close to each other. That might end up having the same position and the same orientations that leads to overfitting or duplicate particle. We can set this number to like 10 or 20 to get rid of the particle that fall within that range. And we also have the generating reconstruction after filtering. What this means to do is normally or personally, I tune the parameters and I get these informations like how many particle left, how many percentage of the particle are clean or kept. And from the log, we just see, and then once I satisfied with this number, I click on this options to generate the reconstruction using the clean particles to see whether or not the features does improve without using the bad particles. And the FSC does not have overfitting or positive correlation at high frequency due to the duplicate particles. And once your data have frames, we can essentially align the motions or estimate the motion across movie frames, but each individual frames is noisier than each individual tilted projections. So we need to be careful and to be aware of it's pretty hard to align because this low signal to noise ratio of each individual tilt frames. So we regularize the noisy trajectory we estimated over the frames, and how we regularize it is first one is we can apply some smoothness on the noisy trajectory over the frames over the time, so it will make it more smoother. And we can also make the trajectory of the neighboring particles similar, so the spatial and the time regularization can kind of smoothen the noisy trajectory a bit, and it can be tuned. So we will to prevent the overfitting. And there are some critical parameters in the movie frame refinement. You need to select these options to refine the motions of the movie frames. And you also need to click on the regularize transition to regularize your noisy trajectory, and the spectral sigma determine the regularization over the time, which is the frames I just mentioned to make it more smoothen. And the the time sigma is the smoothness over the time over the frames to make it more smoothen, but the spatial sigma is kind of like regularization over the trajectory and its neighbor of the particle and its neighbor. Right. And once you have the reconstructions, you want to sharpen it using some B factor. It can be done in the post-processing block. You can kind of create the post-processing block in particle refinement or the movie frame refinement as long as you have reconstructions. And once you tune your parameters, you can visualize your results in the reconstruction and tab that where you can see the sharpen map, sharpen reconstructions, and the unmasked FSC and the masked FSC with the shake mask. And you can also simply apply the shake mask you created in the upstream processing to the post-processing block. Also, in order to improve the map resolution, we want to control the contribution of each tilted images because the tilted images do not have the same quality or same resolution, high resolution informations due to the increased sample thickness during the tilting and the accumulated electron damage. So we can apply the data-driven exposure weighting here in particle refinement block or movie frame refinement block. And in that block, you should see the weights coming out if you turn on these options in the reconstructions. So on the left-hand side, you should see the plot like this. It is the average similarity score we compute using by comparing the particle projection and the reference. And if we plot the score, average score over the order of acquisition, and the order of acquisition depends on the tilt scheme you use. You can see if we kind of use the dose symmetric scheme, you have higher score in the beginning of the data acquisitions. And then by converting the score we obtain on the left-hand side to the weights we essentially use for the reconstructions, we can get the weight. And this is controlled by the parameter I'm just going to mention. And the x-axis represent the frequency, y-axis represent the cumulative weights, essentially the portion or the percentage of each tilted projections contributing to the high resolution. And each band represent one tilt images. So if we draw a vertical line on the right-hand side, which is at high resolution, is mainly contributed by the first few tilted images, which makes sense because we want to use the high resolution information from the high quality images. And there are some critical parameters as well. You need to, in the particle refinement block or the movie frame refinement block, go to the exposure weighting tab, and you have to enable the dose weighting options. And there's like two critical parameters controlling the shape of the weights. One is frame weight fractions, and this parameter control the number of the tilted projections contributing to the high resolution. The higher the higher the value is, the fewer the particle projection will be contributing to the high resolution. So if I use 4, it would have this weights. For example, if I use 8, you will see fewer images on the right-hand side or at high resolution frequency. Another one is frame weight transition, and it's kind of control the transition of this curve from high resolution to low resolution. And you can use these two parameters and also visualize the weights to control what kind of weights you want to use or use in the reconstructions. And just be aware of, before the movie frame refinement and the movie frame refinement, we essentially have different kinds of average score and different kinds of weights. So on the top is the per tilt score, and on the bottom is the per frame score. Each has different score because after the movie frame refinement, we get the score from each individual frame instead of individual tilts, so it will be noisier. And even using the same set of parameters like a transition and the fraction parameter I just mentioned, you cannot cover or recover the same weights used for the reconstructions. So usually after switching to movie frame refinement, you need to tune these two parameters to and visualize the result to better extract your high resolution information contained in the data. And in the particle refinement panel and the movie frame refinement panel, you should always see these three tabs that you can visualize the reconstruction. I'm gonna talk about this or demonstrate this tomorrow in the practical session, but essentially in the reconstruction tab, you can download your map, you can go back to the previous iterations, you can go to the last iteration very easily and visualize the projection of this of the reconstruction or the central slice, the average of the reconstruction easily to see whether the feature does make sense. And in the resolution, you should see the unmasked FSC between the two half maps. And if you have multiple iteration, you should see multiple unmasked FSC. And you can get a better idea how the distribution of the orientation and the defocus looks like, but just need to be aware of they are in the particle projection level. It will be like each data point will be one particle projection instead of one particle. And you can get the statistics of this refinement, such as the one of the rotation and the distribution of the defocus or the score you might get, and also need to be aware of it is in a per particle projection level. And here on the right, bottom right, you should see per particle scores is in the per particle basis. You can use this to determine the threshold in the particle filtering block by removing the bad particle which have a bad score. And go to the exposure weight tab that I just mentioned. You can see the average score over the order of the acquisition, and also see the weights in this block. And it should be like per tilt series basis. And then go to the 3D view tab. You can see the 3D maps very easily. You can choose two different maps from different iteration in the same block. And we also offer simple operation that provided in the Chimera, such as tuning the contour level, adjusting the threshold of the density maps, and change the level of details or change the color. You can put the two maps side by side, or you can superimpose them together to spot the differences in the map. Okay. Okay, so here are some results on HIV-1 gap proteins using our proposed structures. And this is the same data set I just mentioned in the scalable data processing framework. By using our strategy, we can improve the map resolution and also improve the map features. And I want to highlight the number of the particle projection and the number of frames. And if you are processing this amount of data, like 43 tilt series, 100K particles, you have to store like 4.1 million particle projection and 41 million particle frames if once we go to movie frame refinement. But now we don't need to store this amount of particle projection using the scalable framework we just introduced. If your data have or protein have multiple conformations, we can classify and resolve different classes using 3D constraint refinement. And traditionally, we classify each individual solve volumes, but it has all kinds of issues like the missing wedge and the storage requirement. We are moving away from the solve volume averagings. We want to classify the particle projections, but without the constraints, without the tilt angles or the geometry, each individual particle projection will be assigned to all kinds of different classes, and it's not a good thing to do. So we impose the constraints, like each particle projection have multiple tilted, each particle has multiple tilted projections. We kind of bound the particle projection together, belongs to one particle, and it will be assigned to different classes more robustly. And you can do the 3D classification in particle refinement block. So particle refinement block is kind of like a super block. You can do all kinds of things. And the prerequisite would be reconstructions and the alignment. So I typically, I have a particle refinement block. I just create a particle refinement block based on the previous refinements, such as reference-based refinement. And there are not too many critical parameters. Go to the classification tab. You have number of classes. And personally, we start by using fewer classes, such as 2 classes, and try to resolve the classes. If you can clearly see they are different, you can successfully resolve 2 classes, and then we increase this number to larger values, such as to try to resolve as many classes as possible. And we do have the similar parameter max resolution that determine the range of the frequency you want to classify. And then in the classification tab, you can still go back to the previous iteration and go back to the last 10 iterations pretty easy in the classification, and go to the last iteration, for example. And there you should see multiple classes. You can hide the classes you don't want to see, or hide them all, or show them all. So I go ahead to disable the class I don't want to see. And in FSC, you can also do the same thing. You can hide the FSC you don't want to see, and I'm go ahead to only show the 2 classes I want to see in the FSC. And also same for the occupancy, that you can see how many particles are contributed to each classes. And you can disable that or hide them all, etc. And in the classification tab, classification block, you can see the class movie. So in this case, we have 8 classes, but they don't have this smooth transition. So we allow you to adjust the order of the classes, to arrange it, to change the order so that you can make the motif move more smoothly to make a movie, etc. And you can change the way it display and change the speed of the movie. So it will allows you to better analyze your classes after the 3D classification. So wrap up with some conclusion. With the pre-processing and also this session, you can see each block in the nextPYP cover different aspects. Some of them is input block, pre-processing, cover different aspect of the cryo-electron tomography pipeline, and the distributed processing. Fashion is used all the time in the pre-processing and also the refinement. You should always see there are multiple split jobs running in parallel. Better use the HPC, high performance computing resources. And during the alignment, because individual particle projection and the individual particle frames are pretty noisy, so we usually impose the tilt geometry constraints, such as tilt angles and the rotation angles, tilt axis rotation angle, to improve the maps while preventing overfittings. And we provide end-to-end user-friendly graphic user interface for data processing. So it will allows you to visualize your result, troubleshoot any issues, and you can flexibly connect different kinds of blocks together to customize your workflow. All right, so that I will take question now.
Okay, great. So we have several questions. One is, can you explain the difference between fully constrained refinement and reference-based refinement?
The reference-based refinement, what is different from the fully constrained refinement? And I know the term is not pretty descriptive, but reference-based refinement is meant to gets the initial particle orientations that, for example, like you don't know the particle orientation, they are randomly orientated, and you don't have reconstructions that you can use to refine the tilt series alignment parameters. So you can get the initial particle orientation in the reference space refinement by using the reference. And we are also having the ab initio, but it will be mentioned or talk about later during the session. But then the fully constrained refinement is used to like locally optimize or optimize the tilt series element parameters and the particle orientations. So it will just do the local optimizations. It will not search globally like the reference-based refinement. I think is I can yeah, should be answered.
Yes, I think there was a question that you kind of like answered already, was that whether you needed to have a reference or not. So you mentioned the ab initio, and we'll talk more about that in the third session of the workshop.
Right.
Okay, so there is a question here that says, can one apply symmetry, like different kinds of symmetry, I guess, to these Cryo-ET reconstructions?
You definitely can apply different kinds of symmetry. For example, like apple ferritin, you have this level of symmetry. We also resolve the structure of the apple ferritin at high resolution that was shown in the previous session. And for the HIV1 gap proteins, which has C6 symmetry, and we can also obtain this structure at high resolution. So you can kind of define, there's like a parameter of the symmetry you can specify.
Right. The next one is, can you perform local refinement using a shape mask?
Yeah, you definitely can apply the shape mask. So don't know whether I think so you can, once you have the reconstructions, you can create a shape mask based on the reconstructions from the previous block. And then in the downstream block, you can like either movie frame refinement or additional particle refinement block. You can get the location of the shape mask from the previous block and apply it to the current block, which can be particle refinement or movie frame refinement.
Right. So there are several questions related to the scores. So maybe we should try to address that. So the question is, can you elaborate on how the scores are actually calculated? And is there a way to verify that the threshold is suitable when there is no separation between when you in the histogram?
Yes. So in tomography, for each particle, you have multiple tilted projection for each particle. So how we calculate the score, I didn't mention this because it's kind of like additional layer, but you have the lowest tilt angles and the highest tilt angles, like a range, and you use the tilted projections within that range to compute your per particle score. And that will be the score shown in this plot. So each data point in the histogram would be the average score. And how I choose a good threshold, ideally you should see two populations. Like this population means the poorly aligned particle or bad particle, or they are not actual proteins. And you can simply select the threshold to better separate these two populations. But if you don't see these populations, that means your alignment may not be good. You can try to align your particle again using more points for the reference-based alignment or different parameters. If you still cannot see it, I would suggest to, like in this case, you barely see the two population, then I would suggest you drop in the middle of the of these mountains, and then we also provide the information on how many particle left. You don't want to get rid of the vast majority of particles, like 50%. So you can kind of use these two criteria to clean your particles.
There is a question about being able to perform 3D classification without alignment, I guess similar to when you do like no alignment classification.
Yeah, we do provide options that you don't have to align the particle. So I believe I didn't show you this option here, but in the refinement tab inside the particle refinement block, you can enable the skip refinement. Then during the classification, the particle would not be realigned or be aligned.
Great, thank you. So the next question is about regarding the command line. So can the refinement steps be run from the command line independently from the nextPYP web server? And if so, what is the format of the input file?
Input file. There are several questions. So the input file I will assume is the parameter files. So each individual parameter will be mapped to the parameter used in the command line, and you have to look into our tutorial. We have the tutorial if you are going to use the command line interface. And for the questions like independently running from the web interface, so I would suggest if you are starting with web interface, you need to do everything in web interface. And if you are starting with command line, you should start everything from command line. If you are like exchanging like different modes, that will cause some inconsistency because we need to store some states or have some figures on the web interface. If you kind of skip some processes, it will not be consistent. And if you are if you want to use the command line interface, we also have the tutorial in our documentation that you can look for.
All right, great. There is a question here asking whether it is possible to do 2D classification, I guess for for projections extracted from tilt series.
Now we don't offer 2D classification in tomography. I believe it is done in single particle analysis, but I think it can be done as long as you have the particle stack.
Yep. Okay, there was a question here about how is the classification actually done, which maybe came before you explained that, but maybe it would be good to like say that one more time.
Okay. So in this diagram, in the B, is using the solve volume averagings, like each cube represents one solve volumes, and we assign different solve volumes into different classes, which is labeled in different colors. But now we are not using solve volumes, we are aligning the particle using the particle projections or classifying the particle using the particle projections. And the one here on the top is without the constraints, and the one on the bottom is using the constraints, like the tilt angles. And you have to think about like each particle projection, each particle has different projections, like from -60 to +60, for example. With the constraints, we kind of bind all the tilted projection for a given particle together. So that would not like each individual particle projection would be assigned to different classes, like the one without the constraints. With the constraints, they are all tied together. They will be all assigned to different classes, the same classes, like the one shown in this diagram. Hope make it clear.
Okay, great. We're almost out of time. I just wanted to say that if you have questions, just put them on the Q&A. That's the only one way where you seem to get answers back to you. And we do have a lot of outstanding questions in the list. Some of them we're leaving for later because they're going to be better answered in the respective sessions. So it's not that we're don't want to answer, but we'll get to them once it's the most appropriate time. The other thing is, yes, and then we're going to try to answer as many as we can, during the breaks or during the session. So hopefully we'll get to to all of your questions. So I think that's about all the time that we have. So now we're going to take like a 35-minute lunch break, and then we will be back at 12:45 p.m. Eastern time. So we will see you all then. Thank you.
Thank you.